Well, first about me, I'm Paul Boom, and I'm a professionally trained ninja and packet juggler. And I have been in security for a while. I recently worked, 2 years ago actually, I worked on quantum cryptography protocols at University of Vienna. And I found it quite interesting how bad the status of protocol development is and how much fun you can have with developing cool frameworks for various protocols. So I'll be talking about TCP/IP hacking tools today and about all the stateless tools that we already have and the fun you can have with them, but also about framework design and in specific about a design for a TCP/IP stack that I've been working on. And, well, to look at the current status, we have lots and lots of cool tools to fingerprint and connect to and send packets to and port scan on a stateless level. So we have Nmap for, and we have tools that do full connect, that use the TCP/IP stack of the operating system. So we have Nmap for scanning using SYN packets and various other scanning modes. We have POF from Mikhail Zalewski for fingerprinting single packets in a stateless way. We have tools which work on fairly stateless protocols like ARP for spoofing IP addresses, for returning wrong MAC IP associations. And they all have in common, they are fairly advanced, they are connectionless, and they operate on a stimuli response level, which means send a packet and wait for answers. However, the limitations of those stateless network tools are quite obvious. We can only scratch the surface of TCP. So after the first SYN that is sent on a connection, if we want to do active fingerprinting, we are out of luck. We can only fairly unreliably determine the operating system that the operating systems that are communicating. Okay. So, okay, those tools can only scratch the surface of TCP. And well, for example, people are trying to work around this. So POF has support for SYN plus X fingerprinting, and also for ECK fingerprinting, but it's fairly broken because the options that get sent along with a packet, with a SYN ECK packet and with an ECK packet, depend very much on the various options that you send with the first SYN. So you have state there. You have state for passive fingerprinting. You actually also have state for active fingerprinting. And also various tools which would be cool, which would be like IDS evasion for any exploit, for any... Well, I just leave it at that. Well, we can't, for example, do a TCP trace route. Say we have an existing connection, say we have a web server, and we get an incoming connection to this web server. It would be fairly cool to just be able to do a trace route over the existing connection, where we could learn information about the net that is on the side of the client. Or we might want to just use an exploit and use IP ID fragmentation techniques like the ones, like the advanced ones Dan Kaminsky presented today. We could want to use that with any kind of applications that we're already using, but right now we can't. We need special purpose tools as soon as any of the tools we want to use become stateful or any Um, well, so what I've been thinking about for a while, for at least since 2001, is that we need a framework to write this kind of stuff. There have been really cool tools written, some released, scanners and various other cool tools that implemented their own TCP/IP stack, but they've always been fairly special purpose. On the other hand, we have really awesome, cool frameworks, even frameworks and tools, even though it's not very much necessary for stateless tools, stateless hacking. So, for example, muxtcp, I will demonstrate it later, is a TCP/IP packet construction, encoding, decoding, and sniffing and sending tool, and it abstracts the whole problem. I mean, in the past, we had to write thousands of lines of C code to construct a single packet or analyze it. And with muxtcp, you can write a complete trace route in about 3 lines or something, so really mind-blowing. But so far, we can't use that for stateful hacking. Yes, another thing that's really interesting is, I think, that everything that you learn about framework design can be generally applied to framework design. And what we learn about writing TCP/IP stacks and writing protocols is becoming increasingly important for peer-to-peer protocols, because it's fairly standard and has become common practice that peer-to-peer applications do net smashing and traverse firewalls in various ways, among them using UDP and leaving the connection. And so many companies developing peer-to-peer technology re-implement TCP over UDP. And it might be really cool for them if they, say, use Python to just take the stack that I'm developing and plug it into their application, and they have a full working, fully customizable TCP stack. Also, I think it's necessary to make some advancements to stateful fuzzing, meaning muxtcp really is cool for testing various network appliances for the security, but we might want to go deeper. We might want to test aspects which are right now inaccessible because they require knowledge of the state. How is it done? Well, we choose an IP address and or a port. We can use an individual port that we run our own TCP/IP stack on, or we can use an entire IP address or a space of IP addresses. Right now, there's no support for that. And if the IP address is used by the host OS, we just block it using the firewall or the port. And if the IP address is unused, we answer the ARP requests ourselves. This really means we implement the whole stack from the driver, from layer 0 up to layer 4. Well, and then we do promiscuous mode sniffing on the Ethernet, and we just look which packets are coming in, which ones are for us. So if we have a layered architecture, the Ethernet driver looks for packets with the right MAC address, and just like a real TCP/IP stack does it. But we are user space, and this makes us very flexible. And then we answer the packets that we receive, and we send our own TCP acknowledgements and so on, but later more about that. So, what protocols are handled, or what protocols can be handled? The framework design that I currently have, which is my fourth rewrite, is based on a paper from 1995. I don't know who wrote it, but you can look it up. It's linked from the talk page on the 22C3 website. It's called a framework for network protocol software, and they originally developed it for TCP/IP and later adapted it for ATM, so it should be fairly flexible. And the way I'm implementing it right now, you have a driver, which is the hardware. You could theoretically have multiple drivers, which passes it on to an Ethernet protocol, IP protocol, UDP, and because of some library decisions which I made. There's even implemented HTTP and Secure Shell and DNS, which isn't integrated yet. So we should be able to handle all the protocols in a few weeks to a few months, depending. Okay, so what is possible if we have a complete stack and for now assume the design is flexible enough that we can customize everything, that we can change everything, that we can build things that before haven't been thought about. So, for example, new tools, things we haven't toyed with before, traceroute over existing TCP connections. Also, we could re-implement many of the man-in-the-middle attack suites using this TCP IP stacks in much fewer lines and much cleaner code. Also, it would be interesting to write an intrusion detection system using a high-level protocol abstraction, but that's been done before, probably. Then we can write peer-to-peer stacks, TCP over UDP, stuff like that. Of course, what also comes to mind is writing honey nets and stuff like that. Certainly would work. Then we can add modules, various kind of states or protocols or semi-protocols to the processing chain that take care of things like automatically adding IP fragmentation attacks to the packets and overlaps. Then we could write the stateful scanner, which can send out a lot of packets, even if no reply comes, without wasting any resources or any ports. We can just reuse ports. We can bend the limits of the protocol as any way we want. Then we can full OS detection, of course. We can just pretend, we can just set the default values of various packets. We, just as the fingerprinting tool do, we can record them and we store them and then we use them whenever we need to. So we can do both passive and active fingerprinting fooling. Also, we could improve OS detection because, as I said, POF only does reliable SYN fingerprinting right now. And I think tools like Nmap probably could also have the limits with fingerprinting because they don't really know so much about the state. Good, so how do we get, send, and process the data? Libraries and programming paradigms that I use. One of them is asynchronous programming, and it works like this. If you set the socket to be asynchronous, it means whatever you do with the socket, it's not going to block. If you try to read from the socket and there is no data to read, it's not going to wait until data arrives, but it's just going to tell you in implementation-specific ways, there is no data here, so try again later. So if we want to wait until data arrives on one or more data sources, we use the select statement or a poll or a KIO. Or there are lots of different ways, operating system-dependent ways of finding out if data arrives on a non-blocking socket. So the way it works with select, which is quite representative, is that you tell it, oh, I have these connections in self.connections, and I want to know for reading, and I want a notification when some data has arrived. In this case, I store the read list, the sockets that are available for reading now, and some other lists after calling select. And then for every socket that has received data, I read the data and I print it out. Fairly simple. If we want to generalize this, however, it's really cool to add a little bit of object orientation voodoo and to create objects with nice callback abstractions. For example, in this case, this is from Twisted, which I will talk more about in the next slide.